In today's lecture, I will talk about infiltration, and you might know that infiltration is one of the most important components of water cycle. And in general, the definition is the infiltration is the process of water penetrating from the ground surface into the soil. The maximum rate at which water can enter to the soil, it is called infiltration capacity. We measure infiltration rate or infiltration capacity in terms of millimeter per hour. It shows something like speed of the infiltration or moving water downward into the soil from land to subsurface soil. So I would like to start with a question, if you can support me with answering this question. Here we talked about the rate of the penetrating, rate of moving or observing water from soil, from water ground, from above the ground to the underground. Which parameters in your mind are influensive in the rate of the infiltration? Can you do you have any idea? Actually, if you focus on this figure, all those important parameters that has influence on rate of infiltration are shown in this figure. At least this expression here, less infiltration in non-porous soils and rocks, or the other one showing here, more infiltration in porous soils and rocks, gives a clue that porous, something like less non-porous or porous, are is one of those important parameters. Therefore, the first parameter that we are going to study is porosity, as defined equal to, or eta. We show the eta denotes porosity equals to volume of voids over the total volume of soil. Assume that we have a sample of soil from here like this. This is a soil skeleton, a sample taken from this part. And you see that maybe you also know this knowledge from the soil mechanics course. A soil skeleton, a soil segment has three phases: air, water, and solid phases. And therefore, and based on the volume or weight of water, air, or each part of this soil skeleton, we can define different parameters. And as you see here, porosity is volume of voids to total volume. So what is the voids? Voids or porous media in this soil are the summation of the volume of air and water. In total, it is called volume of voids, and total volume of the soil is the total volume of, total volume of sample, not soil. Well, actually, the soil or solid parts has its own volume. This is solid part, but total volume of sample, it is called total volume. And if you divide volume of voids by total volume, it gives you porosity or eta. The other important parameters are, for example, presence or absence of green surface on ground like this, or the rate of precipitation is also important. Water table level is also important. Topography of the land is also important, and so on, some other characteristics that we will see during this lecture. So let's continue with more definition about other parameters that we calculate when we are going to study infiltration. But here we have a note that the range for eta is usually around 0.2 to 0.75. It says that, for example, the volume, because it is in terms of percentage, the volume of voids could be between 25 to 75%. Okay, here in this figure, we will talk about soil moisture, or also called water content, but let's come back to the different part of a soil sample. As I told, we have air, water, and solid parts in a soil sample. As I already told, the summation of volume of air and water gives us the volume of voids. We have volume of solids, and summation of volume of voids and volume of solid parts is called total volume. The same concept is used to define both air weight, water weight, and solid weight. And if you add air weight to water weight, it gives you weight of void. And if you add weight of void area to solid void, it is total void. But weight of void is not generally used in hydrology or soil science. Okay, with respect to the volume of water or liquid in the soil sample, we define another parameter which is called soil moisture or water content in a sample. As you see here, theta equals to volume of liquid water, this volume, to the volume of total sample or total volume. It is called soil moisture, water content. And we can increase, that volume of water due to infiltration can increase, or due to evaporation or suction from roots of plants, it can decrease. Okay, therefore, volume of water during the time is a varying parameter in the soil sample. If volume of water increases in this sample, in that way that we have no air in the system, in the soil sample. Therefore, we can say this sample is saturated because there is no air. So in that case, volume of air equals to 0 and volume of voids equals to water volume. Yes, volume of water. Here you see that volume of water over total volume equals to theta. If we say that volume of liquid water equals to volume of voids, it gives us the same formula that we talked about porosity, and therefore we can say that when theta equals to eta, because the numerator of this fraction will be the same, even volume of voids or volume of liquid water. Therefore, we can say theta equals to eta, and I already told this sample is saturated. Therefore, in saturated condition, we know that soil moisture or water content equals to the porosity or eta. And let's say impervious, let's assume that there is no water. What does it mean? It means generally dry soil. And if due to the, for example, evaporation process, or as I told, suction of roots of plants, there is no water in the soil. It is called dry soil. So what will be happen? Volume of liquid will be zero. Yes, volume of liquid will be zero. It is the minimum possible volume for water at this soil sample. Therefore, the minimum value of theta equals to zero. And so we can say that zero theta, or volume of liquid water, varies between 0 to eta. And when it is equals to the 0, we say this is a dry soil because no water is there. And when theta equals to eta, this is saturated soil. Okay, so there are also some other definitions, including gravimetric water content. In hydrology, we usually use water content or volumetric water content, which is called soil moisture, and we define with this theta. However, in soil mechanics, you might have heard about a gravimetric water content, which is more or less the same, but a special difference between the denominator. When you consider weight instead of volume, it is called gravimetric, okay, because of we consider weight. And gravimetric water content equals to mass of water over mass of solid part. This mass over this solid, it is called gravimetric water content, and we show it with W. And volumetric water content, theta, we already talked about it. We have also bulk density. Bulk density is the density of solid part to, mass of density we know equals to M over V, mass over volume. If you consider only mass of solids, but divided to the total volume, it is called bulk density, and we show it rho sub B. And density of water, you know it from fluid mechanics, is the mass of water over the mass volume of the water. This is called density of water, that you know it is about 1,000 kilogram per cubic meters. Okay, so we are talking about infiltration, and from the different terminologies that we already defined for water cycle, we had another process which was percolation. You had in your midterm exam, and we said that percolation is the infiltration, deep infiltration to the groundwater. So therefore, there is an area that water moves or infiltrate. That area is called Vedas zone or Vedas zone. It is between the land surface and the water table, this area, okay? It is called Vedas zone. Water in the Vedas zone has a pressure head less than atmospheric pressure. It means that there is a suction or negative pressure, water pressure we have. This zone includes, it is important to us because of several reasons. And this is the zone that we investigate infiltration. This upper part of Vedas zone is called root zone, the zone that root of trees are available, and water available or infiltrated water at root zone can be absorbed by roots of trees or plants, and then can be transpired, or even at this zone can be evaporated, then comes back to this cycle of the hydrology. You see that in this zone, it is possible that water moves downward on porous media, or as a result of regular porosity of the soil, or if there is macro scale pores or fractures, water can move very easily. And as I told, the lower limit of Vedas zone is water table. This is water table. Water table is the location of groundwater level. From below the water table, we have groundwater. And water that you here, we have another zone. You see that it is called capillarity fringe, is the part of the zone that water moves upward from groundwater, actually moves upward from groundwater due to the capillarity effects of those very tiny pipes between the soil gradients. So also this part, also Veda zone is important because there is air. As I told, in this area we have air and water, and because of having air in this area, this is the area that burrowing animals can live. And in general, as a civil engineer, this zone is important for us because of the groundwater management issues. How much water infiltrate into the groundwater from the land depends on the features or characteristics of the Veda zone, or in case of there is a release of contaminant on the ground, and the rate of the penetration of those contaminant flow to the groundwater is again is a topic that needs to be studied at Veda zone. Okay, any question? Okay, let's continue with the two other definitions, field capacity and wilting point. Here you see, you know that field capacity is amount of soil liquids, amount of liquid moisture or amount of moisture that soil can keep it within it after getting saturated. You know, when the soil gets saturated, somehow extra water, if you drain the soil again, rain on this soil again, extra water will be drained, but there are a part of an amount of water remaining in the porous area that it does not drain from the soil due to the gravity effect, for example. This water, the amount of this water is called field capacity, and this is the water that plants are used for their growth or for transpiration process. And if we have no more water for plants or the water amount is less than field capacity, too much less than field capacity, there is a condition that the root cannot absorb water from the soil. It is called wilting point. And also here I have a video from this link, you can find it, that Prof wrote here from University of Uppsala, introduced very well field capacity and wilting point. Let's watch this movie together.
I will now show two very useful concepts related to soil water storage. Field capacity and wilting point. Field capacity tells how much water a soil can retain against the effect of gravity. And wilting point gives how much water is left when the plants have sucked as much water they can for their transpiration. This is a sponge that we can regard as a soil. It has very high porosity and it has also a good ability to retain water. I'm now raining on this soil, a pretty big rainfall. All this infiltrated water is stored in the soil, and we can see it as it is stored in the upper part of the unsaturated zone, the root zone. The rain continues, still all water is stored. It becomes wetter, of course, and heavier. Den blir blötare och blötare förstås, lite tyngre. Nu. Now the dripping starts, and after a while the dripping stops. Och efter en liten stund så slutar det droppa här. Now we say that the soil is at field capacity, the maximum water content that can be held against gravity. Further rainfall on the soil will now result in outflow of the same amount. We can say that the soil is loaded. Rainfall on such soil would give percolation of water towards the groundwater. What we can see and hear now is the groundwater recharge. When the rainfall stops, the soil keeps this water content. The plants can use a part of that water while waiting for the next rainfall. They are developing a negative pressure to suck the water. I cannot create the suction, but we can say that this water is what is taken up by the plants. It should, of course, have gone upwards. Eventually, the pressure of the remaining water is so negative, the water is so tightly bound to the soil, that the plants cannot suck any more water. Then the soil moisture is at wilting point. There is some water left, mainly bound by adsorption, but it cannot be used by the plants. The water we just saw falling down is the plant available water that the plant can take up and send to the atmosphere. I'm wetting this soil once more. The water infiltrates, increases the soil moisture content, and eventually reaches field capacity. Vattnet infiltrerar, höjer markvattenhalten. Och så småningom uppnår den fältkapaciteten. Now, some extra water will give abundant dripping. Then I turn the soil, and now the dripping stops. If I raise it, the dripping starts. Så ska vi se om det börjar droppa. Ja. Då droppar det ur den. It seems as if the field capacity depends on the orientation of the sponge. When standing, it can retain less water than when lying. For water to leave the sponge, the pressure of water at the bottom has to be equal to that of the atmosphere. I'm now wetting it in a lying position. Now it's dripping. It is now at field capacity. The water has atmospheric pressure at the bottom, and we can call it the groundwater surface. The pressure of water above equals the distance to the water table. At the top, about 2 centimeters above the water table, the pressure is about -2 centimeters. This is the most negative water pressure of any pore in the sponge now. But if I turn the sponge, a lot of water is drained, and it corresponds to the water in some of the pores in the upper part, where the pores are exposed to a pressure of about -10 centimeters, making also the somewhat smaller pores to be emptied.
Okay, so very well described definition of field capacity and wilting point, and also the professor showed how the pressure varies within the soil or weather zone with higher negative pressure at the top of the soil and lower negative pressure when we reaches to the saturated part of the soil. Okay, now let's continue with the process of infiltration and a bit more about the affecting parameters on the infiltration rate. As you see here, when we have a infiltration process, we can draw such a graph which is called a wet front or wet front, and this shows wet zone of a soil. At topsoil when we have rainfall event at topsoil but underground, this is what we have. First we will have saturated zone, okay, saturated zone, and then water moves again downward but with a less content. As you see here, water front will be closer or will be narrower. We will have a transmission zone, and finally a narrower part of the soil sample will be wet, which is after transmission zone it is called wetting zone. So in general, though, the important parameters, as I already mentioned them and we studied so far, some of them are precipitation rate, soil types, water content, vegetation cover, and ground slope. When we talk about soil type, it is a measure that shows the amount of possible voids between grains or between aggregate. So you see in this in this figure that when we have a finer soil like clay, infiltration potential is lower at finer soil, therefore we have higher runoff. It means that infiltration rainfall is low, infiltration rate is low, therefore most of the rain can transform to the runoff. By contrast, in the coarse materials or coarse soil like sand, we have higher infiltration. It means that most of rain can infiltrate into the soil, therefore amount of or potential surface runoff will be less in comparison to the finer soil. Typical basic infiltration rates of soils are also given in this table. You see, for example, if the texture or soil texture is sand, infiltration rate can be about 30 to 50 millimeter per hour. However, for example, for fine soil like clay, the infiltration rate will be very, very low, like 1 to 5 millimeter per second. Okay, these are some information that we need to understand infiltration process, but how we can estimate it for different type of soils. I gave you some values here. For example, if it is sand, it is in this range. If it is clay, it is in this range. If it is the mix of different soil textures, the range will be different. So how we can find these ranges? Therefore, we need some methods, either physical methods or either experimental ways to estimate the infiltration rate. One of the most, there are generally three, so many methods, but three well-documented methods that we have in hydrology are Horton equation, phi index, and green-amped method to estimate infiltration. In this lecture, I only covered the Horton equation, and the others you can study in your textbook. Horton equation is the one that we mostly use in engineering application. And based on this equation, here, let me provide more informative figure. Here you see the Horton equation that says instantaneous infiltration rate equals to a formula. One given value, Fc, plus another parameter. Let's see what are those parameters. Ft, actually this curve, this nonlinear curve shows infiltration variation. We know that during the rainfall, as I told, precipitation or precipitation rate is one of the important parameters in infiltration rate. So if rainfall, we know that rainfall also varies by time, therefore infiltration is not a constant value during the precipitation. It can vary from the maximum value at the beginning to a constant value at the after or middle at the or during the rainfall if events. The Horton says that instantaneous infiltration rate equals to this Fc. This is Fc actually. Fc is this value, or certain value, or F ultimate final when the infiltration remains constant by time, plus F0. What is the F0? F0 is infiltration capacity or maximum infiltration rate, which is at the beginning of the rainfall event. So if you have Fc and F0, you can use this formula. And we have also e to the power of minus kt. K is called decay coefficient that shows how this curve decreases by time. It is called decay coefficient. And if you know the Fc, F0, Fc or ultimate infiltration rate, F0 the maximum ultimate infiltration rate, and if you know the K, which is the decision or decay coefficient, you can find infiltration at any time with respect to this formula. So the question at Horton equation comes to this type. So from where we should know the value of Fc, F0, and also K. These are the parameters that are determined empirically in the field by doing some tests or by measuring the real infiltrate rate of a soil. Another important point in this curve is the total infiltration. Okay, well, if we have this hyetograph shows rainfall event. Actually, we have a rainfall. This term for this height is in millimeter. For example, 10 millimeter rainfall at 1 minute. Another minute, another minute, another minute, and the rainfall hyetograph shows how rainfall varies. During the rainfall, we know that infiltration also varies. For example, if after 1 minute, if each bar shows 1 minute, after 1 minute, this infiltration, this rate is the infiltration rate of the given soil that this curve belongs that soil. So the area under this curve or this area, if you find that area, it gives you total amount of infiltrated water into the soil from this rainfall event. How to calculate the total amount of infiltration? As I told you, you should find this area, and you know that area under curve means the integration of that curve. So if you take the integral of the Horton equation, this is Horton equation, or this one you saw in previous slide, and it varies between the 0 to 2. If you take the integral of that equation, it gives you total volume of the infiltration, water infiltrated rainfall, or total infiltration water, infiltrated water. Let's take this integral. We have a constant, therefore integral of this constant. My integral is in terms of the time, therefore for this term the result is fc times t. This is a coefficient of e to the power of an exponential function, e to the power of minus xt, and for this part of integral I will have 1 over k multiplied that coefficient, again multiplied by the same e to the power of minus kt. So if you substitute the values of t and 0 at this equation and make simplifications, you will see that this equation will provide you the total infiltration at time t, or capital T. Okay, to get more insight about this formula or this method, I'm going to show you an example from your textbook. The example says that the initial infiltration capacity F0 of a catchment is estimated as 4.5 millimeter per hour. Okay, F0 is given. The time constant, which is again a decay coefficient, is 0.35 per hour. You know, 1 over hour is the dimension of k, and the capacity of the capacity or field capacity or infiltration capacity or maximum or ultimate infiltration value is 0.4 millimeter per hour. Fc therefore is given. And now using the Horton equation, the question asked find the instantaneous rate of infiltration when at 10 minutes, at 30 minutes, after 1 hour, after 2 hours, and after 6 hours. And also in the part B, the question asks us to find the total volume of infiltration over the 6-hour period. Assuming continuously unbounded condition, it means that what we rain, we have infiltration. There is no ponding above the ground. Okay, the answer, to find the answer, we come back to the Horton equation and we replace the given values at the main equation. Fc is 0.4, F0 is 4.5 millimeter per hour, and decay coefficient is is 0.35, and we have minus in the equation. So after 10 minutes, because we are looking for millimeter per hour, the answer would be in millimeter per hour infiltration rate. Therefore, after 10 minutes means 1/6 of the 1 hour. You can put this value here, then calculate Ft, or infiltration, instantaneous infiltration, equals to 4.3 millimeter per hour. After 30 minutes, which means half hour, this value. If you put 1, the infiltration is this, and after 6 hours, it is your infiltration rate. So you find instantaneous infiltration rate at given times. In order to find total infiltration, as I told you, should take integral of this equation, and we already took that integral and we achieved this equation. Therefore, I just put the value of k F0, FC, and total our time, T6 here, and this total will gives us the infiltration, total infiltration in terms of millimeter, because as I told here, that this area is total infiltration, and when you multiply millimeter per hour, the unit, or it turns the millimeter. And this is why here we have 20.7 millimeter of infiltration. Any question? Okay, if there is no question, I just continue with our remaining question, and then we'll end this lecture. You know, again, in this example, we saw that F0, Fc, and K is given, and therefore it seems that if we are going to use Horton equation, we always should know it about our soil sample. It means in reality about the ground where we are studying. And to calculate, to find or to determine these parameters, as I told, we should do experiment in the field. And here I'm going to show you how we can determine those parameters. To determine those parameters in the field, we use an instrument called infiltrometer. We have two different kinds of infiltrometers, a single ring or double ring infiltrometers. Well, how they work? They work very simple and very easily. We just put this, these are just a cylinder, a single ring or double ring cylinder. We put it on the ground and push it into the soil, then fill it with water. Then we check how much water decrease in the cylinder by the time. And after, for example, 1 minute, 2 minutes, 10 minutes, 1 hour, 2 hours, we can measure the amount of water or decrease in the water into the cylinder. Then we can do some mathematics on those data that we taken in the field to estimate these three parameters. Let's see an example that we did in our university. You might know Özgün, who helped me in hydrology course during last years. Here you see that we have a double ring infiltrometer, and we put it in the yard of our university on the ground, and then we fulfilled it by the water. And Özgün measured how much water decreases by having a ruler here. He measured the amount of the decreasing water at different times. For example, after 5 minutes, 10 minutes, 20 minutes, up to 5 hours, he controlled how water decreases. And then he find these points, and he used ruler with the degree of, or with the resolution of centimeter. Therefore, our graph is in terms of centimeter, and the results will be in the terms of centimeter per hour. And you see he derived such a graph. Each point here shows amount of water decrease in versus time. And finally, you can fit a curve like this easily in Excel, or even you can connect those points together. This curve is your infiltration curve. And if you have infiltration curve, and if you know that, you see this is very close to this curve is very close to the curve of Horton equation, that we have such a curve. And here we know that FC is a ultimate or final infiltration rate. We know that F0 is initial infiltration rate at the beginning of experiment. Therefore, from these points or from this curve that you fitted to the points, you can easily find F0 and FC. For this soil in our university, we found that F0 or initial infiltration or infiltration capacity is 66 centimeter per hour. Look, this point stands here, about 66 centimeter per hour. And our experiment showed that the last, after 5 hours, and you see that this curve will continue very close to or adjacent to the 30 centimeter per hour. And this is why we say this is ultimate in infiltration. And from this graph, we concluded that FC equals to 30 centimeter per hour. Now in this equation, I have FC and F0, and the only unknown parameter is K. To find K, what we should do, we come back to the table of records, the table that we provided this graph. This is our table of records. You see, after, for example, 10 minutes, half hour, blah, 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 we measure different drop in the ring, in this, our infiltrometer. And these values are cumulative values of infiltration. It means that after 0.17, let's say about 10 minutes, we saw that 11 centimeter drop in the ring. After 0.33 hour, we saw it is the drop from the top is about 19.7 centimeter and blah, blah, blah. We have this table during the measurements. And infiltration rate equals to drop per time. So if you divide this value to this value, it gives you infiltration rate in terms of centimeter per hour. So you have this infiltration rate, which is your instantaneous or FT. We draw, yeah, FT, and you saw these values here. So if we come back to the Horton equation, we can rewrite this equation in a way that Ft minus Fc equals to this value. I mean that I moved Fc to the left side of the equality. Therefore, I have such a term, Ft minus Fc. Ft is instantaneous, I had it, and Fc, I already found it equals to 30 centimeter per hour, yes? So for each given Ft, I can find Fc, which is simply 66 minus 30, or 31.2 minus 30. This is my left-hand side of this equation. And I showed it by A. Therefore, I can, in this side, I have F0 minus Fc. I can represent it by B, as you see here. And then this Horton equation can be shown like this. A equals to B times e to the power of minus kt. Okay, now the time is for the calculation of B, or this parenthesis. We know that F0 and Fc is a constant values, and F0 minus Fc equals to 40, F0 minus 40, it is assumed to be 40 here, okay, to be 40, a constant value. But for this experiment, F0 minus Fc, it should be 33, okay? So then we have there are some measurements in these values, but anyway, this column should be constant. If you have such a constant value, you can find from here, you can say that, okay, A equals to B times E to the power of minus KT. You can find E to the power of minus KT equals to A over B. Yeah. If you take the logarithm or natural logarithm of this equation from both sides, ln of A over B will be equal to minus K over T. Okay, now I need to calculate A over B and then take the natural logarithm of A over B. This is my A over B values. A is this column, B is given column, and these are my A over T. And if you take Ln values, it gives you this term. And you can say that for you have this equation for different at different times we have A over ln A over B. Now I draw another graph. And I say that, okay, I assume this is my y-axis, t is time, it shows my x-axis, and this equation is something like this. Y equals to minus x times t, a line, yes, a line or a linear curve. And if it is a line, minus k should be the slope of that line, yeah, and minus means that the line has a decreasing slope in the with respect to the x-axis. So to draw that line, I can use Excel again. You see, I put this. I can do different ways, but to find this K. Using Excel, I can show these points again for given t. This is my t-axis. For the given t, y equals to this value. For example, one y is here, the other y here, here, and this curve shows you the continuous location of those points. And if you fit a line on this curve by adding a thread line in Excel, you will reach such an equation, y equals to minus something times x plus or minus a given value, a given value. And this is actually the slope of this line or thread line that we fitted to our data. And you see that our fitted line has a good accuracy of r square equals to more than 0.98. So the k value or the decay coefficient equals to 0.64. That taken. Now I have F0, Fc, and K for this soil sample, and therefore I can guess, you see this sample shows more or less a uniform condition here for this area. And I can say that, okay, infiltration rate at this area can be represented with such equation that Ft equals to 30 plus, we assume this is 40 or 33 e to the minus of e to the power of minus, we found what? 0.64 times t. It is the infiltration rate for infiltration equation for this area. Yeah, that's all for today's lecture. And actually, I would like to ask you if you are interested in this topic and if you would like to do or accomplish your senior project in hydrology, make a contact with me, and we are an ongoing project in our university that my master student Tuğçe is working on it. It's about infiltration, and she does a similar experiment that I explained here. If you are interested to join her and to join my research team, please make contact with me, and then I will manage how you can enter into the project. Okay, that's all for today. Please go ahead if you have any question.